Hello, everyone. Welcome to ICANX Talks. I'm Lan Fu, a professor from Australian National University. So today we'll start the first talk for November. And in November, we have a theme in soft matter. And we have 4 excellent speakers for ICANX Talks. They are Professor Dragomir Neshev from Australian National University, Professor Aaron Wheeler from University of Toronto, Professor Rong Chen from Huazhong University of Science and Technology, and also Professor Qibing Pei from UCLA. So let me first introduce our speaker for today's ICANX Talks, my colleague from the Australian National University, Professor Dragomir Neshev. Professor Dragomir Neshev is the director of the Australian Research Council Center of Excellence for Transformative Matter Optical System, TIMOS, and a professor in physics at Australian National University. He received his PhD degree from Sofia University, Bulgaria in 1999. Since then, he has worked in the field of optics at several research centers around the world and joined ANU in 2002. He is the recipient of several awards and honors, including a highly cited researcher by Web of Science in 2021, a Queen Elizabeth II Fellowship in 2010, and a Marie Curie Individual Fellowship in 2001. His activities span over several branches of optics, including periodic photonic structures, singular optics, plasmonics, and optical metasurfaces. So the floor is yours, Dragomir.
Thank you, Lan, so much. So let me know if you can see my screen.
Yes, we can see very well. Please
okay.
Go ahead.
It's a great pleasure to be with everyone today, and I would like to tell you in my talk today a bit more about tunable optics with dielectric metasurfaces. This is one of the key research activities in our Center of Excellence in Australia. And with this activity, we want to replace existing optic to make it more functional, more dynamic, and more useful for everyone. So before I start any further, I would like to acknowledge a number of collaborators that have contributed to this talk and to these research activities. Most acknowledgements and most focus goes to the 2 bright students, Khosrow Zangeneh Kamali and Zivei Yang from the Australian National University, together with a large team of collaborators at the ANU, as well as my collaborators at Nottingham Trent University, University of Brescia in Italy, and the University of New South Wales, Canberra, Australia. So before we start, I would like to say a few words about metasurfaces, such that we all know what we're talking about. So metasurfaces are a sub-wavelength array of nanoscale optical elements, and the periodicity between these elements, or the spacing between elements, is much smaller than the wavelength of light, as you see here. And because of this, the light actually sees these metasurface as a homogeneous material, however, with material with new properties that often do not exist in nature. Just a few examples of this you can see here. This is a plasmonic metasurface made out of gold, as well as silicon dielectric metasurface made out of amorphous silicon. And such metasurfaces can cause a large light confinement. They can capture the light, and they can re-emit the light with required phase, polarization, and even color. And in my talk, I will focus mainly on the electric metasurfaces that has been the workhorse for our activities in the past couple of years. With metasurfaces, their potential is the ability to miniaturize optical components, while at the same time adding more functionalities, squeezing more, packing more in a smaller space. And you can see that this is addressing an existing problem now with optics. As we see, most of the phones, the optics is the thickest part of the phone. And every phone wants to pack more displays, more cameras, more lenses, and so on. And the fact that these lenses currently are made from bulk glass does not allow us ultimate miniaturization. In addition, one might want to add LiDAR type functionalities of image recognition, which would add more and more to the optics that has to be packed in a small space. Therefore, we are desperately in a need of small and miniaturized and highly functional optics. That is the topic of the Center of Excellence that I work with. Just another example, this is a drone that has an environmental camera on top. It's an infrared camera that looks for environmental features. Unfortunately, this camera weighs like 1/3 of the body of this drone, which prevents the drone to be able to fly in a large distance and so on. Therefore, again, we need something that we can miniaturize, especially in the infrared imaging, where the current optics is even worse than in the visible optics as you see in the phone. So this is where meta-optics really can make a big impact. Meta-optics based on many nanostructures that are packed together to make a function, to make a particular function, as you see here as a lens that focuses the light in a single point. And such optics can really transform a number of industries, like transport with LiDAR technology, health with wearable optical sensors, defense with night vision, education with holographic displays and augmented reality, communications with light speed, Wi-Fi technologies, and remote sensing using infrared and quantum type light. The power of metasurfaces is coming from the resonances that are excited inside these nanostructures. So the physics really is based on exciting resonances that can capture the light, similar to the fact how a drum can capture the sound of sound waves that can be re-emitted. So in a similar way, the nanostructures of metasurfaces can capture light inside and really concentrate it and release it with the right properties that we can use later on. So the most used resonances to date has been the so-called Me resonances, which are based on the very well-known Me theory by Gustav Me, which was discovered more than 100 years ago. And Me has provided an important insight of the scattering of small nanoparticles. The fact that this scattering is defined by two coefficients, which define two families of modes inside the electric nanoparticles. These are electric type modes where the electric field oscillates in the nanoparticles. So this is a geometric type mode. So the size of the nanoparticle is equal to the wavelength of light inside the nanoparticles. And this could be the fundamental and the higher order mode, being the dipole and the quadrupole mode, respectively. At the same time, there is another family of solutions that coincides together with the electric type, which is a magnetic type mode, which are happening due to the oscillations of the magnetic field and corresponding circulations of the electric field in the nanoparticles. Again, note that the electric field really is geometrically confining the nanoparticle itself. So this is the important thing to note, that these Me modes are really geometrical modes, and their size is equal to the wavelength of light inside the nanoparticle, or multiples of wavelength of light. So even though this theory was developed more than 100 years ago, the first demonstrations of light scattering of nanoparticles, the electric nanoparticles or nanospheres in the visible, in the infrared region, was only actually proven about 10 years ago by two groups, by Arseny Kuznetsov and Andrei Yevlukhin, showing this scattering and the appearance of electric and magnetic type modes in the visible spectrum. So this has been done more than 10 years ago, and these days the range of modes that we're seeing in metasurfaces have been extended to more and more modes, including the so-called bound state in the continuum modes, which allow us to have much higher Q factors of resonances in comparison to the Me modes. So in the bound state in the continuum, one can explain them as modes that have symmetry which is oscillating, like as we see here, positive and negative amplitudes. And the Fourier components of these modes have zero Fourier component at normal incidence to this to the metasurface or photonic crystal slab as was originally proposed. So because of this symmetry of the modes that is oscillating up and down, these modes cannot really radiate to plane waves at normal incidence, and therefore these modes remain bound inside the structures. They cannot radiate. And even though other type of modes, so we have an infinite amount of other types of modes, which are depicted here as odd modes, which exist in the entire frequency spectrum. However, these modes are the even type modes are discrete. They cannot radiate into the normal incidence, and therefore their quality factor can approach infinity. In practice, such quasi-bouncer in the continuum modes can be excited, and most of the groups today demonstrate few factors of the order between 100 and 10,000. And you will see how these very high quality factor modes will become very important for the topic that I will see today. So because of this very large number of modes, the amount of metasurfaces that we see kind of in the literature in the recent days has dramatically exploded. Effectively, what we are seeing is from a realism of small spherical or cylindrical nanoparticles, we are seeing a surrealism of different structures, as what you see here is a free topology optimized structures by Jonathan Fenn from Stanford University, or dispersion compensated structures from the group of Federico Capasso, or amplitude and phase three-dimensionally modulated structures from the group of Stefan Meyer and our opponent here today, Hauran Ren. In addition to these large and different types of geometries, we are seeing also an explosion of different materials that are being exploited for metasurface type optics. And these are, for example, lithium niobate material, which has strong electro-optic properties, gallium arsenide, which is a semiconductor, can be changed with charge carriers, or hafnium oxide as a material that is very transparent in the ultraviolet. And similar titanium dioxide, which is becoming a material of choice for visible wavelength, visible spectrum optics, as we see here, one metal lens fabricated by Capasso's group. So this type of meta-optical elements have been a focus of research in the past couple of years. And what we are seeing now is that these elements actually are projecting their power of design of new types of optics to new type of devices. So these days, in the last couple of years, what we are seeing is that the majority of research in meta-optics is being focused on devices that can show new functionalities based on the elements that we saw before. So such devices could include flat lenses, polarization routers, microscopy cover slips with special functions, biosensor, and so on. And of course, the top of everything is that these devices actually project to powerful applications that can really transform our lives. So these include like 3D imaging, AR, VR, glasses and displays, holographic displays, LiDAR type technology, and image classifications. All of these belong to so-called vision application, but we are seeing also a number of other applications beyond vision that are coming into play, like, for example, light sail, like metasurfaces that can be used as a sail to propel small satellites in space with very fast velocity. Because of this large number of applications, what we are seeing is that also a large number of big companies are starting to develop research activities and products even to adopt these technologies in their practices, in their products. And I believe in the next couple of years, we will be seeing practically in every phone or in every car, we will be having a piece of metasurface under the hood of the car. So what is, however, important that many of these applications that I pointed out that the optics that we have can be dynamically reconfigured and tunable. For example, for holographic displays, we want to see movable images. We need to have some tunable type of optics. Same with LiDAR and so on. And so therefore, the topic of tunable metasurfaces really has become at the forefront of development in this field. And there's a large number of activities that we're seeing at the moment that various groups in the world are taking in order really to put metamaterials and metasurfaces into the active domain such that they can be actively reconfigured and dynamically modified. There are two types. We can sort the tunability of metasurfaces in two types. Tunability of the amplitude of the transmission. So this is important, for example, for adaptive color displays, where things that we want to see like on our phone, that we can have different colors that can be changed. And you see here an example of colors that can be changed by applying electric field in a liquid crystal type infiltrated metasurface. However, something that is probably the most powerful in this field is to be able to provide phase tuning of the transmitted light, which empowers a number of applications such as LiDAR technologies or holographic displays. At the end of the day, the ultimate goal, what we want in this field is really to have a fully programmable optical functionalities coming out of a metasurface. What do I mean by fully programmable optical functionalities? This is we have an element that we can dial in what we want this element to do, and this element will do that. So if you want the element, a flat surface to be a lens, you can dial it and it will be a lens. If you want it to be a hologram, to give you a hologram, it will be a hologram, and so on and so on. So this really gives us a completely new opportunity, a completely new vision how we look at optics, and optics that can be really changed in anything that you wish. But before we get there, we need to really do the bottom groundwork, how we can tune, how we can provide the tunability of metasurfaces. Again, arrays of closely packed nanostructures. In practice, there are three main concepts that can provide tunability of metasurfaces. These concepts are based exactly on the fact that the resonances that are excited in metasurfaces are geometric type resonances. So therefore, if we tune the material, so change the refractive index of the resonator material, refractive index of these red type resonators, we can correspondingly change the optical path inside the structure. Therefore, we will be tuning the metasurface properties or the metasurface response. Similarly, if we infiltrate the metasurface with a homogeneous environment on top, tuning the surrounding environment can provide us a second path for tunability. And finally, changing the geometry, but by actuating geometrically the spacing, like here in this case, stretching a flexible film of a metasurface can really give us another type of tunability. In my talk, I will focus mainly in the first two approaches. However, these approaches can be done by different types of mechanisms. And there are large numbers of physical mechanisms, tuning mechanisms that can be employed to achieve these approaches. And here are just a few examples like electrical gating, photocarrier injections, thermal effects or phase change materials, again, to thermal effects, mechanical actuation, magneto-optic control, modulation of the surrounding environment, which I mentioned before, chemical approaches, and optical nonlinear tuning. Which one of these tuning mechanism will be really important or will take over is still unknown. So there is a very big active research of activities on different mechanisms, and different groups are trying to show which mechanisms is really most promising. But probably the truth is that in the future devices or future applications, we will be seeing a large choice of mechanisms being used, and the choice of a particular mechanism will largely depend on the applications. For example, if one needs a very fast tunability, then maybe electric gating and electro-optic type effects are really the one to have. if you need a strong tunability, then maybe thermal effects and mechanical actuations is really what is needed. In my talk, I will focus on two particular examples, so modulation of the surrounding environment and modulations of the resonator material through thermo-optic effect. We have done quite a bit of research also on phase change material, however, I will not touch base on these activities today. So the outline of my talk in the next minutes will be, we'll discuss first the possibility for realizing amplitude tuning with programmable functionalities. And second part of the talk will be focused on phase-only tuning of the electric metasurfaces, where I will show you the physics behind how we can do that. In particular, the two-mode operations that we need to achieve for such tuning. And we will show you a little bit of kind of opportunities to do that using liquid crystal infiltrated metasurfaces. So let's start with the amplitude tuning of transmission, and I will focus on this by thermo-optic effect. By thermo-optic effect, I mean that we will be heating the metasurface, which will be changing the refractive index with temperature, which will be changing correspondingly the resonances of the metasurface. So coming back to the resonances, if you have a resonant metasurface and you illuminate the metasurface with a polychromatic light, what we will see is that some part of the spectral components of this light will excite the resonant modes. These components will be reflected back, while the rest of the light will be transmitted through the metasurface. So then if we measure the transmission spectrum of the light through a metasurface, what we will see is a transmission dip, which is the feature of this resonance, the feature that part of the colors in the spectral region are being reflected. So when we want to tune the transmission geometry of the metasurface, what we want to achieve is to tune this spectral dip from one wavelength, the initial wavelength, lambda naught, to a new wavelength, which is lambda naught plus this delta lambda. So in this case, what we will be seeing if we have a laser that is operating at this wavelength lambda naught, we will be seeing that the transmission of this laser will be modulated from low transmission to high transmission. So obviously, the take-home message from this simple consideration is that for an amplitude tuning of metasurfaces, a single mode of excitation inside the metasurface is sufficient, and one can modulate the mode by changing the transmission dip towards blue and red shift. There is one more thing to it, and the thing is, as I mentioned before, the quality factor of the resonance. So if the resonance is broad, for example, in the case of Mir resonances, and we provide some tuning mechanism that shifts the spectral dip to a new wavelength, at this delta lambda, we are seeing small modulation of the laser that is operating in the initial wavelength. However, if instead we use a metasurface with a sharp resonance, such as in the resonances of bound state and continuum, what we can see is that the same shift of the resonance actually causes a much larger change to the transmitted intensity of the laser that is illuminating the metasurfaces. So the take-home message is for high Q metasurfaces, the amplitude modulation is significantly stronger than for low Q metasurfaces. That's why a lot of research has gone into really looking at employing high-quality resonances metasurfaces. And you see here two important examples, and they're important because they're electrically driven type examples. Therefore, what I mean is that we have two contacts, as you see here, where we drive a current, so electrically controlled current, where we can change the properties of the metasurface. This particular example is based on phase change materials which are heated through the current that is propagating through the metasurfaces and is changing the materials. In this case, GST material is changing through different phases of these materials. Unfortunately, with the phase change materials, the most kind of common ones that are really easy to operate with smaller voltages, like in this case, just a few volts. Such such phase change materials have very high absorption in the visible and near-infrared spectral range. Therefore, as you can see in this graph, the phase change materials are more suitable towards infrared, like shortwave infrared and mid-wave infrared type applications. However, not so good for a visible type application. For near-infrared applications, more recently we have seen the realization of such special light modulators based on electro-optic effects in polymers. So this is from Federico Capasso's group, which is a very fast modulation. Again, depending on the applied voltage here between these two electrodes, one can shift the resonance to positive and negative frequency. And this is really good example. It's a very fast modulation. However, these polymers, the electro-optic polymers that are utilized here, are relatively difficult to really employ in end-user devices. And the modulation depth that we are seeing here usually remains low of the order of 20 to 30%, as we see here. So in our work, what we wanted to do is to be able to realize fast modulation with low tuning voltage, so voltage that is compatible to consumer type electronics like plus minus 5 volts, what you have in your USB type devices. And we wanted to do with conventional materials, but not using any unique or exotic materials like the polymers, as I showed before. So what we found out is that we can achieve a lot of this just using the thermo-optic effects in silicon. So silicon has a very large thermo-optic effect, and one can check this by shining a light onto a thin film of silicon that is on a transparent substrate. So for example, you can take a SOI wafer and you can shine a light through this material and measure the light that is going through the material versus wavelength, what is this axis here, versus the wavelength that is illuminating. So you take a spectrometer, so you measure the spectrum, and what you will see is these Fabry-Perot resonances based on the thickness of this silicon layer. So now if we start heating up this silicon layer, you can see that all these resonances are shifting dramatically to the right, to longer wavelengths. And this is because by heating the silicon, we are changing its refractive index. We're increasing its refractive index. And just from this simple experiment, one can plot the refractive index or variation of the refractive index of the silicon versus temperature. And that maps extremely well to the available models that you can find in the literature. And what you can see is that just for a few hundred degrees, one can change the refractive index of the silicon over 0.2 refractive index difference. So this is quite dramatic just from a simple heating of a silicon layer. So we thought this must be a really good way to approach and to test this with metasurfaces. And the first experiments that we did, driven by Mohsen Rahmani, at that time at the ANU, we use a silicon disk metasurfaces, which are mere resonance, as you see here. And we used the electric heater, which is just placed next to the metasurface, which we heated up to 300 degrees. And then we measured the scattering or the transmission through such a metasurface and looking at the resonances that are being excited. So in this plot, what you see here is two spectra for metasurfaces with two different diameters of these disks. One is for small diameter, 170 nanometers, and the other one is for large diameters. So in the small diameter of the disk, we are hitting the first order mid-type resonance. And what you see here, before the heating, we have this black curve. And after heating, we have this at 300 degrees, we have red shift of the curve, as you see here in this with this red plot. We could cycle this back and forth quite a few number of times, and this is absolutely reproducible, so it's a very good idea. but the shift of the resonances was practically the same. So it's about 30 nanometers to the right. And this didn't change if we go to high order resonances. So low order, high order resonances, they all shift in the same way with the same amount of shift, spectral shift, for the same heating range. So that was good. However, if you look at the transmission modulation that one can achieve in this the resonance regime for these metasurfaces, this was relatively low. So the next thing that we wanted to do to improve that was exactly the idea of going and utilizing a resonance with a very high quality factor instead of a mid-type resonance metasurfaces. So for this, we again use a silicon disc metasurface. However, we made a small hole in the silicon disc. So the silicon disc is very thin in this case, just 30 nanometers. And because of this small hole, we are exciting a quasi-BAC mode. So the cylinder, it has a magnetic mode, which is effectively oscillating of the electric field in the circle of the cylinder. However, this magnetic mode, which is a MZ type magnetic mode, cannot be directly excited. However, the presence of this small hole, which provides a small electric dipole that couples to the magnetic mode, and this small electric dipole excites the magnetic mode in MZ. And because of this, we are seeing a strong phonotype resonance, which effectively in transmission, these are the measurements that are being done in transmission, gives us a very sharp resonance at around 800 nanometers with a quality factor about 100 for these parameters that are listed here. So then the next question is how we can do something useful with tuning these such narrow band resonances. So in order to make something useful, we decided perhaps we can do some sort of images or paintings based on metasurfaces. And you see one of such painting that we have created, a famous yin-yang symbol. To do this, what we did was to create two types of metasurfaces, resonant metasurfaces. One named A, type A, which has a resonance at the operating wavelength, which is this green line here. So for this operating wavelength, the transmission of the light through this A-type surface is slow. And you can immediately guess that this part, the dark part of the yin-yang symbol, is made out of these A-type structures. At the same time, we have another type of structures, type B, which is has a resonance that is blue shifted with respect to the operating wavelength. So what this means is that if we heat the resonance here, of the structure A, the structure A will redshift and will go out of the resonance, while the structure B will go into the resonance. And as you can see here, this white area here is composed of type B type resonances. And I just want to play quickly this video. So what we are seeing, we have the metasurface with type A and type B resonances, and again type B and type A here. And now we're heating up this metasurface, and what you will see is that type A, which was initially dark in transmission, will become more transparent as the resonance shifts into the operating wavelength, while type B will become less transparent. So the yin-yang symbol switches its colors, and then if we cool again the metasurface, we again revert the process and get to the original situation. You see here just the three specific type of these images at 22 degrees Celsius, at 75 Celsius, where both transmission through both types is practically the same, and at 125 degrees Celsius. So what the bottom line here, the take message is that by employing these high quality factor resonances, we can modify this transmission with a much lower heat required than in the previous example where we required over 300 degrees. Now we have reduced the required heat just over 100 degrees Celsius. So however, this was good. However, this was all heated with one big resistor, so we didn't have any control of the individual pixels of the metasurface. And something, as I mentioned to you, what we really want to do and what is really important in this field is to be able to demonstrate or to realize a multi-pixel metasurface that is programmable with small applied voltages that are compatible with end-user electronics. So to do this, we had to demonstrate a multi-pixel metasurface, and we generated this based on 3 pixels. And the 3 pixels are controlled by 3 different electrodes. So we have 3 different electrodes when you run current through the metasurface. However, the first problem that we could see in this case was that we want this metasurface to operate in transmission. So if we have electrodes, these electrodes will be absorbing the light. So we needed to incorporate transparent electrodes in order to heat up in the individual pixels of the metasurface. And what could be better than for transparent electrode than ITO? So because of this, we incorporated ITO on top of it as a transparent conductive oxide as an electrode, where we could run current and control this current from the individual pixels. The metasurface itself is a membrane type metasurface, which has a bound state in the continuum resonances. The bound state in the continuum happens from the fact that one of the holes of the metasurface is smaller than the other hole, as you can see also here on this schematic. And we use this membrane metasurface not just because it has the sharp bound state in the continuum resonances, this case with quality factor of the order of 50, but also because the continuous film allows us to have a good heat conduction through the entire metasurface. So, and then we drive this with a small electric field. The first thing to do was to apply the electric field through one of the pixels and to see how the resonance frequency changes. And what you see here is the transmission measured through one of the pixels at 780 nanometers. So we have a resonance initially at 780. And when we apply a 4-volt voltage across the electrode that drives these pixels, what we could see is that the resonance shifts now from the blue curve to the red curve. So we have 12 nanometers of shift just by applying 4 volts across this metasurface. So this is a very good achievement because we have a very large contrast of the transmission. However, what is also important and what we need to be tested is whether we can drive this with a speed that is at least a video rate type speed. So we can create a display type metasurface. So for display, for just a normal display, you need all the pixels to be able to switch on and off at the video rate. So in order to do that, we driven this metasurface with this voltage that is shown here in blue curve. So what we are seeing here is that we are applying a small spike voltage at the beginning. This small spike voltage allows for fast heating of the metasurface in order to heat the metasurface before the cooling effects which happen through conduction into the substrate happen. So by using this spike voltage or flash type heating, as we call it, we could see that the optical transmission power changes very fast, very abruptly at the beginning, then remains the same. And then when we switch off the voltage, we have the standard cooling off of the metasurface, which happens through conduction into the substrate. So if we zoom in on this forefront, what we're seeing is that because of this spike voltage and the flash heating, we can drive this rising front of the modulator effectively rather fast. So the rising end of the pulse in this case is 625 microseconds, so sub-millisecond type rising edge, while the trailing edge of the pulse, which happens through natural heat conduction, has the order of 20-25 millisecond kind of time scale, which effectively allows us to drive this at the video rate with over 90% modulation of the metasurface. And now the next step, what we needed to demonstrate is how we can switch these with different rays. We can switch the different pixels. In our case, we only have 4 pixels. This was the maximum weight what we can drive with our drivers. We just use a FPGA card with 4 ports, and we drive the 4 different pixels. So what you see here is initially we applying current through these first electrodes. So the electrodes with the current are marked with a solid dot, and we see here this electrode is changing from bright to dark. Then we apply into the second one and so on. So what you can see here, how we're switching the transmissions of the different pixels, and we can cycle this quite a lot without any degradation of the device. Of course, one needs to make a point that if you drive these pixels constantly, eventually you will reach a thermal equilibrium where all these different pixels will be in the same state. So in order for this device to operate, one will need to switch on and off the pixels in order to allow for the natural cooling. However, this could be mitigated by adding active cooling or implementing small grooves in between the pixels to reduce the crosstalk of the pixels. So the take-home message is that just by using the simple thermo-optic effects in silicon, we were able to demonstrate a multi-pixel control metasurface, which is driven by voltages that are compatible with end-user type electronics, and is showing over 90% of modulation of the amplitude. So now I will switch gears a little bit, and we will tell you in the next 15 minutes, we will tell you a bit more about phase tuning of metasurfaces. And for phase tuning, one will need to incorporate 2 types of resonances where we have, as you see here, a so-called Huygens condition. And I will demonstrate this kind of phase tuning by the second type mechanism that I discussed, which is by tuning of the environment. So first, what is a Huygens condition? So I mentioned at the start that the electric nanoparticles have 2 types of resonances, electric and magnetic type resonances. For spherical particles, these resonances happen at different frequencies. However, if one uses a disk type geometry, by changing the aspect ratio of the disk, one can overlap the electric and magnetic modes together at the same frequency. And this is what you see here. So the electric and magnetic modes that are coming together at a particular wavelength, they overlap, at which this is the transmission through the metasurface, at which the transmission becomes very high, so unity. And if you start changing the disk radius again, you are again splitting the 2 modes. So what's happening here in this overlap region? So this is effectively a crossing type, crossing of 2 modes. And this crossing happens because these electric and magnetic modes effectively orthogonal to each other. So they're not hybridizing as in the usual case of other modes where you have avoided crossing. Here we have a full crossing of the modes. So what is good, what is interesting here, that at the position of the crossing, what we are seeing is there's just a forward scattering of the metasurface, which gives rise to this very high transmission. But at the same time, because we have 2 modes, and each mode has a pi phase shift across the spectrum of this mode. So what we are seeing here is that we are accumulating a 2 pi phase shift if we are operating in this position of the overlap of the 2 modes. And this position is called the Huygens condition. And these are the 2 modes that are being overlapped here. So electric and magnetic modes, and you see they have rather different nature. However, they are fully orthogonal and they give rise to this high transmission with 2 pi phase shift. So the experiment that was demonstrating this was done in my group nearly 10 years ago by Professor Staude, who was at that time with us. And what she did was to measure the transmissions of such metasurfaces, which are fabricated on silicon on insulator, by changing the diameter of the metasurface. And you can see here these great demonstrations of the Huygens condition. So you have initially the two modes for small diameter, which are well distinct between the two. They come together in a particular diameter. The two modes effectively overlap. At this position, the transmission goes practically to unity. And if you continue increasing the diameter of the modes, you again see the splitting of the two modes again. So this is very good because in using this Huygens condition, one can put disks with different radii such that they all operate in the Huygens condition, meaning high transmission close to 1. But because of the different radii, they impose a slightly different phase on the transmitting light. And using this type of Huygens condition, one can encode any static phase profile with very high transmission onto the metasurface. However, the big question is, if you want to tune this Huygens condition, as we know this is composed of the two modes, you will need to have mechanisms that to tune the two modes together in order to preserve the Huygens condition. If we don't preserve the Huygens condition, the two modes will split together and we will see a dramatic drop in the transmission. This is also illustrated here now in a particular example of liquid crystal infiltrated metasurface. So the two modes come together, we have very high transmission, and we reach the Huygens condition. And this is what we wanted to explore in our research, to explore liquid crystal type tuning with the Huygens condition in order to create a phase-only modulation for spatial light modulator type application. So for those of you who are not familiar with liquid crystals are effectively liquids composed of very elongated molecules. These molecules vibrate, but however, they remain mostly aligned. And the alignment of the molecules together, because of their large dipole moment, they remain aligned. These are called nematic liquid crystals. So in the solid state, they're fully aligned as a crystal. However, in the liquid state, they have some disorder. However, in generally, all the dipoles are aligned in the same way, creating a liquid with a very strong dipolar moment. This liquid can also be driven into the isotropic phase if you increase the temperature further. And by increasing the temperature, one can see that one can dramatically change the refractive index of this liquid. And we have two refractive index, so ordinary refractive index for light that is perpendicular here to the screen along this arrow, or the extraordinary refractive index, which is for line that is aligned with the long axis of this director. And so the question is, can we use this voltage type tuning of the liquid crystal modulation together with this temperature tuning of the refractive index change of the liquid crystal in order to maintain the Huygens condition and to achieve a phase-only modulation. So we started these activities quite some time ago, and the first thing was to model this liquid crystal as an isotropic medium. So we put it in silicon discs in isotropic medium in a liquid crystal cell, which is 4 micron thick, and we are operating in the Huygens condition. And so what we did in this theoretical work was we estimated this refractive index versus the tilting of the liquid crystal molecules, and then we calculated the transmission spectrum for these liquid crystal cells. So what we saw that the transmission at 15-18 nanometers remain relatively constant, about 80%, as we see here, or between 80 and 90%. And the phase, which is effectively the accumulated phase, which is effectively the angle along this polar plot, effectively changed really from 0 practically to 2 pi. So this was very exciting initially. However, when we did a bit better analysis, we saw that only half of this phase comes from the metasurface. The other half comes simply from the light propagation of this long crystalline cell here, which is 4 micrometers in this case. However, for any practical device, you want to reduce this liquid crystal cell to the smallest possible case, so micron or submicron type liquid crystals. So therefore, one would need to get rid of this simple propagation phase. So then we were a bit discouraged because we could not make the phase to be 2 pi with a unity transmission. And then we started learning more and more and trying to understand what is going on. So first thing we did was to demonstrate the tuning of the two resonances, the electric and magnetic type resonance versus applied temperature. So we could see here that by applying temperature up to 60 degrees, we can shift the resonances until we enter this isotropic phase transition. We also applied voltage across the top and bottom surface of this liquid crystal cell, and we measured transmission with respect to the applied voltage from 0 to 70 degrees, and you see here the phase tuning. So what we see is that we are obtaining a phase that is of the order of pi, as we predicted before in our theoretical work. However, this phase tuning of 3 pi over 2 was coming at the expense of a large amplitude modulation. So because of a 29 nanometer shift of the electric resonance and 55 nanometer shift for the magnetic resonance. So we didn't know at that time what to do. So we thought, okay, maybe a good device could be just to encode the static phase by changing the radius of the disks, and by tuning the liquid crystal by temperature at cold and hot temperature, the pneumatic and isotropic phase, to tune the transmission through such meta-grading type device. And indeed, we saw this, that what you see here is the output transmission of light at the design wavelength. So I believe this is at 1550. And we see here that initially at room temperature, all the light is in the 0 order of diffraction. And once we increase the temperature, we are switching the energy of the light between the 0 and the first order. So many works, even at that time, we thought, oh, this is very good for beam steering, for LiDAR type application. However, the only thing that this is doing is switching between the 0 and the first diffractive order. But what one would really want is to be able to continuously switch the position of the beam all across the transverse angle. And there have been a large number of activities trying to do that. And the one that comes as close as possible is the work from the group of Arseny Kuznetsov at the A-Star in Singapore. And they use this type of resonant metasurfaces, so the mid-type resonant metasurfaces. They found this unique condition that for a particular wavelength in the visible spectrum, they could obtain the 3 discrete phases, 0, 45, and 90 degrees, without any transmission modulation. So this was really groundbreaking. However, only allowed for 3 discrete phases and wasn't really scalable to more discrete phases to be added. So at that point, we were asking ourselves, is it possible really to tune the phase continuously without this discretization? And we needed to understand how this is possible. We need to dig a little bit deeper into the physics of liquid crystal infiltrated metasurfaces. So one thing that is very important, and that kind of has been neglected in most of the previous work, that the liquid crystal is in an isotropic material. So for liquid crystal that is oriented vertically here in this cell, the refractive index will be given by 2 ordinary, 1 extraordinary component. So effectively what we have, what one can see here is that we have two different types of refractive index that potentially we can tune separately or independently with some weighting across along between these two refractive indices, ordinary, extraordinary refractive index. This is what we saw. So if we have 2 resonances, electric and magnetic resonance, that cross at a particular point, once we change the X refractive index, so the ordinary refractive index, we see that mostly the electric resonance is being moved. This is because the electric resonance interact mostly with these X-type fields here. If we, however, now change the Z component of the refractive index, the extraordinary component, we will see the inverted situation. So we will see that mostly the magnetic resonance is being changed, while the electric resonance remains practically constant. So this was interesting and opened the possibility that we tune both NX and NZ, where we tune the NX with some magic constant which is proportional to NZ, and to achieve that both of the resonances are simultaneously tuning with the change of the refractive index, simultaneously tuning here with the change, so we can effectively achieve a constant, a gradient phase kind of accumulation with this tuning without really disturbing the condition, the Huygens type condition. So this was good, but the big question is, okay, the devil is always into the details. How do we do that? In order to do that, we employ the so-called extreme Huygens metasurface. So this is the same thing like a Huygens metasurface. So it has two modes, magnetic and electric modes, except that these modes are very high quality factor resonance. So they're quasi-BAC type modes. Because they're quasi-BAC type modes, so again, we can have this unitary transmission, but the phase change could be made very sharp or smoother just by tailoring this angle of these ellipses in the metasurface. So changing the angle from small angle, we have very steep, sharp change of the over 2 pi of the transmitted phase with unitary transmission. If we go for a larger angle, like 30 degrees, we have much smoother change in the phase. However, we also see some accumulation of the oscillations in the transmitted spectrum. So this was good. So we tried to test, using this kind of Huygens condition is good. And we tried to test how we can tune this with the employment of the idea that we mentioned before. So if we just tune as before this, if we take this structure and tune just the ordinary refractive index of the liquid crystal, we see the usual condition. However, if we now tune both the X and the Z and X refractive index together, we see that we have these two modes that are completely overlapping, and we have a unitary transmission over a very large wavelength range for the entire this tuning range that we have of the index, and the phase indeed accumulates from 0 to 2 pi. And this magic number R is really magic. It's 2.78, which we don't know where it comes, but it was giving a really good result experimentally. This was for a case of a metasurface that is practically homogeneous on top and bottom, so it's suspended in the liquid crystal. In reality, the metasurface is sitting on the substrate, so this substrate is causing asymmetry of the metasurface, asymmetry of the geometry, top and bottom, which kind of makes the situation slightly worse, but still we have a very large, relatively large bandwidth of operation, 5.3 nanometers, comparing to the isotropic case, the case that all components are tuned with the same rate, which is only 1.75 nanometers bandwidth. So this kind of idea allows us to have a broadband Huygens regime by tuning the resonances at the same tuning range based on the anisotropy of the surrounding environment. So then, but doing this in practice was even more complicated. So obviously, in order to hit this magic rate, we needed to have two parameters that we tune. And one option is to have a three-dimensional tuning of the liquid crystal. So this is my second last slide. And the second option is to use two independent parameters, which is voltage and temperature. So for employing these two independent tuning parameters, we made a map for different temperatures and different voltages, and we found this plot here. In this plot, what we could see is that there is a magic voltage which preorients the liquid crystal at a particular angle here, for which if we tune the temperature, we get unitary transmission, as shown here also, unitary transmission with nearly 2 pi, slightly under 2 pi phase modulation. And so this is operating for a bandwidth of 3.5 nanometers, which is sufficient for picosecond type pulses and maybe even for long femtosecond time pulses with such a phase modulator. Importantly, the two resonances shift with the same rate in this case, and we have the full 2 pi range, so for which can be tuned homogeneously with unitary efficiency. The second effect that we thought, so this was an interesting approach. However, it's very difficult because the electric field in such highly inhomogeneous environment of high index dielectrics and liquid crystals is also very inhomogeneous. So the second approach that we are currently working on, this is just a quick glimpse of this idea, is to use a magnetic field to tune the liquid crystals in 3 dimensions. And in this tuning of 3 dimensions, the application of magnetic field is very important because we have non-magnetic materials, and the magnetic field effectively is always homogeneous inside the liquid crystal cells and allows for such tuning. So you can see some more details here in this work. Because I'm running out of time, I will stop here with the conclusions. So I hope I show you some, at least the initial stages of something that has a big vision of achieving tunable devices using metasurfaces. We're using amplitude tuning with programmable type metasurfaces was the example, and phase only tuning using liquid crystal type modulation with 2 parameters, or just 3-dimensional positioning of a magnetic field. So with this, I thank you all for listening today and looking forward to your questions.
Thank you so much, Dragomir. It's a great talk. So can you please stop sharing, and so that I can start to introduce our panelists tonight straight away. So our first panelist of the ICANX talk tonight is Dr. Zhexing Huang from Leibniz Institute of Photonic Technology. Dr. Zhexing Huang is currently the head of the research department of nanophotonics at the Leibniz Institute of Photonic Technology in Jena, Germany. Dr. Huang is also a principal investigator in the epicenter of photonics at Friedrich Schiller University, Jena. His current research focus is on the engineering of nanoscale optical fields using rationally designed nanostructures for the control and enhancement of light-matter interactions. Our next panelist is Dr. Haoran Ren from Monash University of Australia. So Dr. Ren is the Australian Research Council DACRA Fellow at the School of Physics and Astronomy at Monash University. His nanophotonic research aims to develop advanced optical materials and nanotechnology for both fundamental light-matter interaction and broad photonic applications. Our ex-challenge tonight is Dr. Angela Barreda from Friedrich Schiller University, Jena. The Dr. Angela Barreda received her PhD degree in 2019 in the University of Cantabria, Spain. She worked as a postdoc researcher at a European project in a group of Professor Martinez at Polytechnic University at Valencia, Spain. And then she was a postdoc with the Humboldt Fellowship in the group of Professor Isabel Strout in Friedrich Schiller University of Vienna, Germany. She currently works in the same group in the framework of the International Research Training Group, MetterActive. And recently she got tenure track position in the University of Carlos III in Madrid, Spain. Her research interests focus on optics and photonics and then computational nanophotonics. In particular, she works on the design of dielectric and hybrid nanostructures that with a wide range of application in such as optical switches, solar cells, and single photon sources. So let's bring our panel all tonight on the stage. Sorry. Okay, so let me just first, as usual, would like to invite our ex-challenger, Angela, to ask the first questions. Please go ahead, Angela.
First of all, Drago, thanks a lot for your really interesting talk. I could learn so many things. I have a few questions for you. One of them is related to the amplitude tuning metasurfaces. So in slide number 22, I think, you showed that the shift in the wavelengths that is caused by the change in the refractive index induced by the heating is possible to use for some painting applications, and show the example of the Indian symbol. And I would like to know if these kind of metasurfaces are possible to use also for other applications, like is the case of sensing, because the resonance are quite narrow, because you are exciting these quasi-big resonances, but still, I think they are not maybe that narrow just for observing some shifts with the changes in the refractive index of the surrounding medium, but not with really high increasing the temperature until 500 degrees or 125, that at the end could maybe damage the sample. So just to obtain narrow resonances to observe a spectral shift, but with a small changes in the temperature.
So, Angela, if I understood correctly, there are two questions. Maybe one is whether these metasurfaces can be used for sensing, and the second one, whether we can decrease the voltage, can decrease the required temperatures to a lower level to avoid damage in the samples. Okay,
Yes,
so the first one is a very good question about sensing, and I usually comment on this, but I didn't today. So thank you for asking this question. So of course, if a metasurface is tunable, that means that if you put some biological or other materials in proximity of the metasurface, that metasurface will change its properties, which one can also measure. So it's a kind of the same, the two sides of a coin. One is the tunability, the other is the sensing. So it's pretty much linked. However, there is a small difference. When you want to tune a metasurface based on the change of the refractive index of the resonators, then you want to have the modes to be confined mainly predominantly inside the resonators. In contrast, if you want to sense a material that is outside of the resonators, like biomolecules or refractive index sensing, you want to tailor your modes to be outside of the resonator. So this is exactly why I showed the two cases of the of tuning with changing of the environment and the refractive index sensing. So for example, and the sensing of changing of the resonate material. So the metasurfaces that I showed with liquid crystals, they're always very, very sensitive on something that is outside, because their modes are specially designed to be outside of the materials. So your second question about the reducing of the temperatures. So this is, I think, limited to the fact how high quality resonances one can do and what bandwidth one would need for the applications. So often in fabrication, due to fabrication imperfections, the quality resonances with quasi-bound state in a continuum are sort of the order of 100 or few hundreds. So it's very hard without making a really high quality fabrication to achieve higher Q factors. So that's why for now we kind of limit ourselves to these temperatures, about 100 degrees. However, they're not particularly problematic, because they achieve only in a small area of the sample, and then it's not heating like the entire sample in that way.
Thanks a lot for your talk. Also, I have other question, if possible. In the phase tuning metasurfaces in slide 35 in particular, I would like to ask if is there any possible way to increase the bandwidth? For example, some ideas that can reduce the anisotropy or increase the tunability of the resonances?
So we did play quite a bit with the bandwidth, and limitations in the bandwidth is really because of the breaking of the symmetry top bottom of the metasurface. So regardless what we could do with the design of the metasurface in the plane, the top bottom sort of could not be really homogenized, and the fact and this is usual because on one side you have a material that is changing, on the other side a material that is roughly fixed with the temperature or the applied electric field. So at the moment I don't know if there are any other opportunities, but I welcome any ideas and would be happy to collaborate with anyone who has some more ideas on this.
Great, thanks, Angela. Before moving to the other panelists, I do have a question from the audience. This is Shenji from Shanghai. Thanks for your wonderful talk. You tuned the liquid crystal by temperature and voltage. Do you think you can do tuning by applying pressure? Will that work?
That's a very good question. I have not heard about tuning by applying pressure. It would depend on the compressivity of the liquid, and I am not familiar with what the properties is for liquid crystals. But thank you for the question. I'll definitely look into it.
Okay, thanks, Dragomir. So now let's move to the other panelists. I can see okay, Zhexing, you raised your hand. Please go ahead.
Okay, so thank you, Dragomir. So very nice talk. I have a few questions. So the first question is probably you already mentioned this. In your tuning with liquid crystals, I'm wondering, is it really that you can change a liquid crystal in the close vicinity of your structure? Because it is typically when the liquid crystal molecule is very close to the structure, it cannot be really tuned. So is this not a problem? I suppose that only the near field of the resonator makes difference. So if the molecule near the structure does not change completely, this would definitely affect the efficiency, right?
Yeah, so this is a very good question. So of course, indeed, near the nanostructures or near the material, there is a certain amount of anchoring layer. So this anchoring layer could be from few tens of nanometers to 100 nanometers. And that usually would reduce the tuning. So you're absolutely right. So this is a problem that is known in the community. It is usually addressed by modifying the surface, for example, by applying a small alignment layer like a polyamide or some other layers, or treating the surface with different materials in order to either charge the surface or remove any charges from the surface. So indeed, this is a problem that is not addressed at the moment, and there is a lot of work that needs to be done to address this issue.
Oh, thank you. The second question is about the bandwidth. You show many nice strategies to really make it sharp so that you can have a very large signal change. But on the other hand, sometimes some applications we want to have a broadband resonance or some broadband application. So do you have any comment or suggestions to make metasurfaces broadband?
So that's very good and very good question, and also maybe more a bit philosophical question. So for phase tuning, it's really hard because then we need to rely on these resonances in order to achieve the phase. It could be mitigated potentially by using reflective type geometries, but again, you need to use a resonant phenomena. With the amplitude tuning, what one can do in terms of making the response broadband is to utilize absorption in the material. So if you incorporate a material that has absorption, you can sort of trigger the absorption, like in the case of phase change material, that one of the phases usually is much more absorptive than the other. So you can make, in one case, the metasurface fully transparent for very broad spectrum. In the other case, absorptive again for a rather large spectrum range. So my feeling is that absorption is the way to go if you want modulation in the broadband.
Okay, thank you. So the next question is a little bit more general. You know, the whole field of metasurfaces comes from plasmonic metasurfaces. And my question is very simple, and you probably also are frequently asked. If I ask you to compare plasmonic and dielectric, there are pros and cons. What could you please briefly comment on in what scenarios would you prefer plasmonic and what scenarios would you prefer dielectric?
Thank you, Zijing. So this is very personal comment from my side, and maybe doesn't agree with everyone. So my opinion is that in all applications that you need high efficiency of transmission or manipulation of light, the electric metasurfaces will always win. However, if one needs to control the emission of either of LEDs or single photon emitters, in that case, the electric metasurfaces do not do very much. They can shape the radiation pattern, but don't do very much. So in that case, plasmonic is really the way to that you can really increase the pulsar enhancement and really change the emission process of the material, including hybridizing with a strong coupling with the emitter and so on. So in that case, in these cases, I believe plasmonic will still remain. And also, I just noticed today, like a very nice paper in Nature, like for free electron laser, based on a plasmonic nanowire, which was really a fantastic work. So again, you cannot do such things with the electric nanowire. So there is, I mean, plasmonic is by far not dead, and it's very active and it's very exciting. And the electric metasurfaces also have a lot of applications that are probably going towards the high-end optics, as we know, replacing the bulky glass optics.
Yes, thank you.
Okay, thanks, Joshing. So, Haran, do you have any questions?
So first of all, thank you very much, Dragomir, for the very fantastic talk. Very interesting. A lot of useful and interesting tuning mechanisms for the flat optics. My question is actually kind of a follow-up of the second question from Joshing regarding this bandwidth, Dragomir. As you reported a lot of high quality factor resonances, metasurfaces, right? But my question is, it's actually like kind of things wanted to acquire your insights regarding this quality factor. As we know, once you have the sharp resonance, the phase change is always very fast, right? So for this kind of a phase, tuning, is there any, compromise between the Q factor and this, I don't know, this tuning sensitivity? Maybe there's somewhere like kind of a balance, right? You don't want to really, slightly change the system and then the phase is sharply changed. Just want to know some insights from you.
This is indeed a very, very good question, very important factor, because in principle, you can increase your quality factor to nearly infinite, and then you can tune very easily with a small kind of stimulus. However, that is not practical, because that is not really, most applications you mentioned require some sort of bandwidth of the application. Like, for example, if you take an LED that is like an LED that is illuminating Face ID from a phone. So this LED has a spectrum of the order of 10 to 14 nanometers, right? So you want your device and your phone to be compatible with this spectral bandwidth. So in that case, obviously the quality factor has to be larger if you want to have a device that is tunable. So it's not kind of a sharp line, but one will need to find the application and then kind of choose the quality factor that matches this application. If the application requires very high bandwidth, maybe then a different type of device is needed, right? So just to give one example, what we do, like we usually will restrict ourselves to quality factor of the order of 100 to maybe 200-300. So this depending on the spectral bandwidth, on the spectral range, will give you a spectral range of the order of few nanometers. And we do that in order to be compatible with femtosecond pulses, because often we do our experiment using femtosecond lasers. And for this kind of reasons, we want all of the bandwidth of the pulses of the femtosecond lasers to be acceptable. So just as a rule of thumb, Q factors of about 100 is a good way to go for many of these applications. But of course, one needs to be careful.
Thank you so much for the very nice answers. Len, do we still have some time to ask you questions?
Yes,
or
go ahead. Yes,
okay,
go
so
ahead.
Maybe I just go for the very last question, Dragomir, regarding this thermal tuning on the silicon platform. You firstly show very nice this tuning effect on the silicon film-based material, and then secondly we move to the particle-based approach, right? My question is, for the global heating, we understand the this thermal effect and the refract index is changing globally as a response of material. But when we consider this kind of nanostructures that they have strong resonances, when you heat up the structure, can we consider this as the global effect, or because there's a strong light-matter interactions, maybe the Q factor is somehow sacrificed when you increase the temperature, or is there any kind of like the nanostructure-based tuning is different from the film-based tuning? Yeah, that's my question.
So if I can maybe rephrase it, your question, let me know if that is the meaning that you have. Is the nanostructuring changing the regime of heating or cooling because we are no longer having a homogeneous film?
Exactly. Yeah, exactly.
Okay, so the good question. So the nanostructures are relatively large for any thermal or kind of electronic kind of effects to really to go on a quantum type level, if you want to say, to be a different process. However, there is one thing that is different, and this is the radiative cooling, or the radiative. When you heat the structure, you have several processes that are playing a role in the cooling factor. One is the convection, which is the biggest one, but then you also have a radiative cooling, which is effectively emitting light outside the nanostructures. And this is where indeed the nanostructuring can have a very dramatic effect. In our case, in the older results that I showed, this radiative cooling is a relatively small contribution to the cooling factor. So I don't know by top of my head, but definitely below 10% of the total effect. So the convection is the main one. However, one can imagine that you can to do similar structures, say on a membrane or on other kind of suspended type devices where the convection cooling is not large. So then this radiative cooling will be very, very important, and that will be an important question really address in the design of the metasurface, whether you want it to radiate efficiently or not. And there is quite a bit of work done in that space. So like people like Shanghui Fan, Nanfang Yu, so they are all working in this kind of along the lines of these ideas.
Perfect. Thank you.
Perhaps I'll also ask the question, Dragomir, if it's possible. Just you mentioned we know that metasurface is fast developing field, and you also mentioned a few very big companies start to really commercialize the technology. So from your point of view, what do you think is really the main challenge to commercialize those very fancy ideas into the real applications?
That is a very good question. So I should say that we're seeing this year like a very good progress in the commercialization of meta-optics. So we're seeing the company Metalens from Harvard, which is really now produce a very large number of devices. But this is not the only company. Maybe this is the first company that is focused on meta-optics, but there are certainly large companies that do incorporate meta-optics in their devices. Like, for example, there are a number of plasmonic color filters that are being implemented in different cameras, or even the Face ID type pattern projectors that are used in current phones. Maybe they're not exactly metasurfaces, but they're very, very close to metasurface type optics. Things are happening, whether we want it or not, because there's a great potential from the technology. But I see for mass production, like one of the biggest issues that I see is scaling up of the research activities that we're having. So most of us mostly use electron beam lithography. Probably Hauran will use also laser polymerization. So these are not techniques that can be scaled on a very large kind of volume production line. So kind of finding these kind of techniques that we can translate and really transition from a lab to factory manufacturing, that is probably the most important issue that we need to solve, and we need to solve it probably together with companies and with industries.
Thank you very much, Dragomir. Do we have the last minute question from the panelists? Okay, Joshing, last question, 2 minutes, please. Yeah.
So just very short. So you mentioned this quasi bound state in continuum. And if it is a bound state, it does not talk to the continuum. If it is a continuum, it is so in this sense, it is because there is no channel linked to the continuum, so that you have high Q factor. But at the same time, you also want to excite that mode. So this is somehow like a contradictory situation. So is there any strategy that you can excite that mode so that it is very intensive, but at the same time still with high Q factor?
So, I mean, the first thing is that's why we always work with quasi-bound state in the continuum mode, because then these are the modes that we can excite. If you want to excite a bound state in the continuum, that otherwise is not open to the environment. So my only kind of suggestion would be to use a so-called time variant approach, like that you kind of use, for example, a very strong laser pulse to open up the mode, and in the short time you couple the energy in, and then you close the mode at that point. So then all the energy remains inside this mode, and then you can use another pulse to read out. So this kind of techniques, I believe Angela has worked in that field as well. So this is probably a possible approach. There are quite a few activities that are going along these lines. So I hope we will see this very successfully as well in near future.
Thank you.
Okay, thank you very much, everyone. That's what all we have for tonight. Thanks again for Dragomir, a great talk, and also the 10 panelists for a great discussion. So now representing ICANX talks, Dragomir here is the certificate. We'd like to really thank you for participating to deliver a great talk tonight. So thank you very much again.
Thank you so much, Len.
Thank you. Next week for ICANX talks, we have Professor Aaron Wheeler from University of Toronto talking about microfluidics for chemistry, biology, and medicine. Please tune in for this great talk next week. Okay, that's what we have tonight. Thank you, everyone, for joining us. Bye-bye.
Thank
Thank
you,
you,
Lan.
Drago.
不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can。能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。能够像我一样飞。